Okay, so this is the quiz. I will send this to Moodle later. And yeah, I think actually for number one, as I mentioned, it's actually a typo for the equation, but somehow we can still try to find the concavity. But it seems that there is no concave upwards, right? So it's all negative, which means that the curve, and I think few students try to draw the curve and it's correct, and they conclude that it's doesn't have any concave upwards. Okay? And then, oh yeah, the second derivative. So I think some of the students, maybe around half of the class, forget this. They just mentioned dx. So dx over dt. Okay. And then what else? I think the second one mostly you got correct. So you could just find equaling to 0 for dy dt and dy and dx dt equals to 0, and you get the horizontal tangent and vertical tangent. You get the t, but it's not finished yet. You need to make sure you get the points. So check the t, and then input to the points, and you get xy. So total is having 4 points. 1, 2, 3, 4. And I think some students missing this 0, 0. So be careful on solving this. What else? Oh, this number 3. The surface area. It's rotated about y-axis. It means that it will be 2 pi x, and then the square root is the arc length. So maybe you could try to calculate the arc length first. You could try to calculate like this one. Calculate this, and then I set up the formulations for quadratic, which it is perfectly square. So you could get this square, and then you can remove by taking the square root, and you get this et plus 1, and then substitute and just multiply. And if you are using your calculator, I think you could just compute this using calculator, and you get around. Either you could use this or compute directly. It's around 1,000 something. That's for your quiz. And yeah, I think probably half of you getting the formulations incorrect. So whenever you have a surface area, it's always 2 pi x the arc length, and then 2 pi y arc length. You can check if this x or y by checking the rotations. So it's rotating y-axis or x-axis. Okay. And how to check whether your thinking is correct or not? You can try to imagine. Okay, here. Okay, if I have this curve, okay, maybe first I will try to rotate to the x-axis. Okay. Rotate this, then we have some circle around this x. Right? It has radius r. Okay, focus on that r. Okay, so this is r, right? Now compare with the y-axis. We have this. Right? We have this radius. Okay. So this x or y is actually our radius. So if we rotate to x-axis, then the radius is y. Okay. And if we rotate to y, radius is x. Okay, so that's why it's x or y. And then you can extend x, y, depends on the functions, okay, the parametric functions. So you could just take x and then using this, right, and substitute, and then you can compute. Okay. And since we are still having the chapter 10 for your midterm, so I hope you get it correct, okay? At least for the polar, Okay, so that is, I will send you this into Moodle for your reference. So we've done quiz 1, and I think we can continue on one note on the polar that I forgot to mention. So this is last time we discussed, right? And I made some mistake here. It's supposed to be -1, square root of 3, and then we define this become -1. Some mistake on calculations, last discussion. Okay, we have the tangents, we have the arc length, we have the area for the polar. Now let me take you into one more note on the surface area. It's not on the textbook, but it is on the problem set. Okay? So if you check your textbook, some exercise, it will mention something related to surface area. So let me start with that, and then if we have time, we can continue to chapter 11. Okay. So surface area. So let the R is function of theta, which between the interval A to B. And then we assume that the f prime is continuous. And then assume the whole circle, or the interval is the half of the circle. So let me assume, and this is important because if we assume a full circle, the other side will have some loops, okay, and then that will be a problem. Okay, we state that if we have an arc length, and if we maybe the drawing having some loops, we need to mention that when the point moves one time, how much is the interval? Because sometimes if we use the maybe interval is more than one full circle, maybe we are making the arc length maybe twice bigger than the original one. Okay? So it's important to assume for the surface area to have this half circle. Okay, and then it's rotated about polar axis. So let me write the general formula for the surface area rotated about x-axis. So in parametric we have this, right? So change to all to theta for the dt. So this is general formula in parametric, and we say it's rotated about x-axis. Now we are going to change the perspective within the surface area from the Cartesian to polar. Okay. Okay, just notes here. Okay, so we get that dy d theta when we learned before, right? We
get the r d theta from the r sine theta, and this is sine, and then plus r cosine, and then the same thing with the dx d theta. Okay, we get that. And then we are doing the same thing as we did in the arc length, which means the arc length, we are going to have this expression. And then taking the square root, right? And then we get that this is r squared plus dr d theta squared d theta. So the surface area becomes s 2 pi r, and y become r sine theta. And that will be the only way we can have. So there's only one type of surface area in which we are going to implement the r sine theta. Okay? Because in polar axis or in the polar coordinates, we only have one axis, or only polar, right? And that's it. The polar calculus in polar finish. Okay. And since on the first week October, I will not be around in Taiwan, so I think I will give you some additional materials, a recording video, and also maybe some assignment that I will put some like an online test, okay? And hopefully you could check that out. But if not, then I will just give you the recording and maybe just a regular homework, okay? Regular homework. Okay, I think we can move to the chapter 11, okay? Sequences, series, power series. Okay, we start with the sequences, okay? For example, this is a picture on, we call this is the Zeno paradox. So what does it do? So we have a one man walking. Let's say he walks every period of time. He walks half of the previous distance. So if he walks 1 meter, the next thing he did is half, okay? And then the next thing he will did is 1/4, 1/8, and so on and so forth. So you will have half, 1/4, 1/8, 1/16, 1/32, and etc. And then he wants to reach the wall. Like for example, if the distance between maybe between him and the wall maybe 2 meters, and he try walking maybe by taking 1 meter, and then the next thing is he will add half, and then the next thing add 1/4,
if you see how can we accumulate these numbers, do you think he will reach the wall? So he maybe, and then the next thing is half of that, and then half, and then half, and I think in calculations he will not reach the wall, right? But if you remember the limit in calculus 1, using limit, you can reach the wall. It's interesting, right? So we call this as sequences. Okay, we call this order here as a sequence, right? So a sequence, usually we set off some lists. Okay, so infinite sequence. So this is a list of numbers written in order, and it must be in order to make it a sequence. Okay, because if it is random, then it doesn't have any meaning, right? So we can write A1 like that, A2, A3, and AN. Okay. And we call the first term, second term, and so on. Okay. Sometimes we can take this order as just this with a curved bracket, or we can add the from which term until which term. For example, from 1 to maybe infinite, because it's an infinite sequence. Or if there's nothing there, it's just like and just like this. It means that assumption end from 1. Okay, start from 1. So our example here, we could thought this as 1/2 with power of n. Okay, if we start from n equal 1, right? Or we can write an equal 1/2 with power of n like that. And then in sequence, another thing that is need to be observed are how to find the pattern or formula. For example, if we have 3/5, okay, I have this set of numbers. Okay, the first thing you notice is maybe the sign first. Okay? The sign, positive, negative. So it has positive, negative, positive, negative, positive, negative. That's one thing. Another thing is the relations on the numbers from the previous term and the next term. So it's 3, 4, 5, 6, 7. So it could be something that is in order, right? And I think in the denominator here, from 5, 25, 1, 25, I think we can also make this a pattern, right? Because if we multiply by 5, it's 25. If we multiply by 5, it's 125, and so on, right? So first we could think the sign value first,
which usually we take these terms or this.
Okay, depends on what will be the first one. Is it a positive or negative? Okay. And then the second one, we could think the number itself, okay, how it's related to one another. Okay.
So we could think from this 3 and 5, and then 4 and the 25. Okay. So if we imagine n is start from 1, it means that we start from n and then plus 2. Okay, that will be
taking the pattern of 3, 4, 5, 6, 7. Okay. And then from 5 to
25. we can set 5, maybe with power of n. Okay.
So 5, 1 is 5, 5 squared, 25, and so on and so forth.
And then we could combine these two and write down that this will be, and we choose the n minus 1, okay? Since we are trying to have a positive term at the first term, and then write down this formula, right? So we can have an equation from some order or some list of numbers. Right? If that is a sequence, then we could figure out how to have a sequence. But not always. Some sequence, they don't have like a simple defined equation. They have a pattern, but they don't have like simplified pattern or equations. For example, if you think the Fibonacci sequence, it's a sequence, right? So we define Fibonacci as recursive. Okay, so define recursively, which means that we start from the first term is 1, the second term is also 1, but the Fn for the definitions is Fn minus 1 plus Fn minus 2, which means that we start from n that is at least 3. Okay, so we could have 1, and then we add this 2, and then add 2 plus 1, and then 3 plus 2, and then 8 and 13 and so on. Okay, and it's not easy to make this into a simplified pattern like this one, but this is also a sequence. You could have a pattern. Okay, and now if you have a sequence, sometimes a sequence can be also visualized into a graph. Okay, sometimes. Okay, let me make it bigger. Let me check. Maybe this one around here. This one around there. Okay, let's go to the next one. Okay. Okay, let's say, let me give you a context here. So, let's say we have a sequence that start from n over n plus 1. And then we can describe this sequence as half, then 2 over 3, 3 over 4, and so on. Or maybe let me add one more, 4 over 5, 5 over 6, and then dot. Okay. So first we could imagine like it start from half. So we could take the interval from 0 to 1. We pinpoint the first term half, and then from this half we could add the second one, which is 2 over 3. Okay, so this is actually with the correct proportion, 2 over 3. This is 2/3, right? So 2/3, and then 3 over 4, and then 4 over 5, and then 5 over 6, and then 6 over 7, and so on and so forth. And then you will see that it's actually getting closer to 1. Right? It's getting closer to 1. So if you remember in calculus, the building blocks for all the relations between how to find derivative and integral is actually limit. We take the integral, it means that we take some area we cut, and then we cut so much that we sometimes makes the n
close to infinity, and we can make it closer to infinity by taking the limit. The same thing with the derivative. We take the limit, right? When we take the point between the two points in the curve, one point we take it closer, and closer, almost close, and we say limit as h getting closer to 0, the distance getting closer to 0, and that's how we find the derivative. Same thing with the sequence. We are taking this, like maybe an, and n is getting infinite. So it has many terms here, but it's never getting 1. Okay. If you look at the picture, because of if you write with your pen, sometimes your pen has a diameter, right? Maybe 0.6 millimeter, 0.8, right? And the smallest the pen, it means that it can be really small circle. Right? And it's the same with your maybe computer or smartphone. It has pixels. Right? This also has pixels. So maybe it's not clear that it is a perfect point. But if you are maybe drawing in a really good graphing calculation, you will see that it will never reach this point. Okay? So we could imagine that if we take this, we start from 1 and then take the limit later, and then we are going to increase n, reaching the infinite. We could see that this limit as n approaching infinity, n over n plus 1, and of course, when you learn limit, you know that we can solve this, and we say that it's equal to 1, right? Okay. Let me get through here. Y is equal to 1 by limit. Okay, so n over n. So this is 1. This is 1. And this is equal to 0, right? So it means that this will be 1. Okay? It's a quick review on calculus. So in general, when we take the limit of some sequence an, it means that it will approach value L. We can also look at the graph on the left. We could also see from this graph that is the x-axis is n, and the y-axis the sequence, the an. So we start from n equal 1, 2, 3, and you see that it's half, and then 2 over 3, 3 over 4, 4 over 5, and it will be reaching at some certain point, it will reaching nearby 1. And then by limit, we could know that it's actually equal to 1, okay? But using limit, okay? So we could start to write the intuitive definition. Okay? We could write that limit. So a sequence has the limit L, and we write the limit of sequence as n getting larger or getting infinite is equal to L. Or we could say a n is closer to L as n getting larger. And then sometimes the sequence, like maybe the example, we change the example, sometimes the limit is not exist. So we say when limit is not exist, we say it's diverges. The sequence diverges. And if the limit exists, we say converges. Okay, so this is sequence. There will be a different, a little bit different relations between sequence and series. You will see, and sometimes students mix up and then take some different assumptions. So be careful on that. Okay.
And how we can make some example on the convergent sequence. So for example, this is a convergent sequence. But look at the end. So we start n equal 1, equal 2, equal 3, equal 4. Okay, not a problem. But then, this goes here. But then, after some certain point at this end, it has consistency. And then we can still say that this will be converged. Okay? The sequence is converged. And later we will know how much n that we need to make this sequence will have a consistency. Also, this one here we have oscillation. Okay? We have oscillation. So the way we look at this, the amplitude is getting smaller. Right? It's reduced, decrease, decrease, and then at a certain point it will getting close by the L. We can also say that this is also convergence. Okay? Okay, and then there is some precise definition that I think I don't want to get into details about this.
But this is just to show you that we can also describe, because within this limit, we can describe the limit by its precise definition, which means we are defining some value and some epsilon that is going to have some relation. So when we have some, so the terms can be anywhere, right? But how much the term is closer to L, that is what we want to know. Like it's close to L, but how much? We are defining that closeness or that distance with this n value here. So this is this
Relations through the precise definition. Okay,
this one describing the precise definition, which gives you the absolute value as an implication of the n.
Okay. And this is an example on
the diverge sequence. Like this one, it goes up and down with the same value, which means it never reach any L. It doesn't have any consistency. We say converge because it goes to at least close to one value, and it's consistent, like close to 1, maybe 0.9, 0.8, or 0.999, and then getting close to 1. Like this one here is getting increase, and increase.
and we say that it never getting
and that is consistent because every time we increase n, it's getting increased. Okay?
so we never getting a converged sequence from that kind of graph. And because in sequence we are basically doing limit, then all the limit laws from the calculus 1, we are going to use it and apply. Okay? And this is, I think this, I will skip this one, this precise definition. So all the limit laws
that is applicable from the calculus 1, we are going to use it.
So basically, to check whether the limit or how to check the sequence is
Converge or diverge, basically taking limit. You have the an, so take the limit. Take the limit, make n approach infinity, and then do the limit. If you get the value, then it means it's getting converged. If not, it is diverged. Okay.
And then another theorem that is related to limit, and I think also important to check, is the squeeze theorem. Okay.
The squeeze theorem, usually in calculus 1, we have three functions, right? Function f, g, h. Now we have three sequences. So the idea from this squeeze theorem is if we can make sure that this Bn is in between AN and CN. Okay, we can calculate the AN and CN. The limit is L. Then, for sure, the middle one also L. Okay, we don't need to calculate the B1, the B. So we just need to calculate AN and CN is L, and we can make conclusion that BN is also L. Okay, but we need to make sure this B is between A and C. Okay. You can see from perhaps this is some examples, okay, how we could see why it is correct. So AN is always down here, okay, and CN also down here. CN also up here, and in between is BN. And you will see and notice that when we increase N, we will have the same consistency here, and that is what the implication from this statement. Okay, another theorem that I think also important is if you have the limit of absolute value of N equals 0, then the limit of N is also 0. Okay.
Do we have time here? Okay. So for example, if we have n over square root 10 plus n, and asking whether it's converge or diverge. So basically, we say that we are going to check through the limit, right? And I think you could guess directly because we are using limit. What do you think is converge or diverge? Is it converge? Diverge. Okay. In limit, if you have like some kind of polynomial function, like a function in some degree, for example, this is degree 1, and this is degree half. Right? Of course, this is greater than this. So, do you agree if I say this will be diverge? So here's the thing. So the idea of limit is basically if we have this is when limit getting infinite. Okay. The first thing we do is we divide with the highest degree. The highest degree is 1. So n over n. But because of the square root, then this will be 10. And then n over n squared. Okay.
So if you take limit on this of 1 over n squared, it will be 0. So some constant 0 will be undefined. Will be the limit doesn't exist, right?
So we can say this or doesn't exist. And we can say that the an is diverge. Okay, if we have another example, maybe the last one before we end the lecture. The Ln, is it converge or diverge? We have Ln n over n.
How do we confirm this? Of course, we take the limit first.
Then we take the limit.
What's the value? Anyone? Remember? 0? Yeah, it's 0. Okay.
So we can take the L'Hopital rule. This means we derive the top and derive the bottom. So this will be 1 over n or 0. So it's converged. Okay. Okay. Okay, I think we can have more tomorrow. Okay, so I will end the lecture and